In this lecture, we will discuss section 13.1 vector functions and space curves. Suppose we have a vector function r of t equals to cosine t, sine t, where t varies from 0 to 2 pi, and we need to sketch it. So here, if you consider the parametric equation, then x is cosine t and y is sine t. So when t is 0, cosine 0 is 1, sine 0 is 0. When t is pi over 2, then cosine pi over 2 is 0 and sine pi over 2 is 1. We are taking points in pi over 2 interval. So if next point is pi, then cosine pi is -1 and sine pi is 0. And similarly, we will get the other 2 points. Now on the xy plane, if we plot this point, then 1 0 goes here, 0 1 goes there, -1 0 is here, and 0 -1 is also here. 1 0 go back that point. Now if we add them, then you will get a circle. And it also has a direction, because when the value of theta increases, it traces this direction. You can also plot this by eliminating the parameter. So here x is cosine t and y is sine t. Now if you square both of them and add them together, then it would be x square plus y square equals to cosine square t plus sine square t. And we know cosine square t plus sine square t equals to 1. So x square plus y square equals to 1. This is equation of a circle, center at 0 0 and radius 1. Now for this example, we have the vector function r of t equals to cosine t, sine t, t over pi, where t is more than or equal to 0. We need to sketch the circular helix. Now when t is 0, then cosine 0 is 1, sine 0 is 0, and 0 over pi is also 0. And when t is pi over 2, so cosine pi over 2 is 0, sine pi over 2 is 1, and this one becomes 1 over 2. And similarly, we will get other 3 points. First point 1 0 0 will go here. Second point 0 1.5 will go there. Third point -1 0 1, it will go -1 along the x-axis and 0 unit along y-axis. That means it's not going anywhere, and 1 unit along positive z-axis. So it will go here. Next point 0 -1 3 over 2 will be here, and this one 1 0 2 will be there. So if you add them, it will be a circular path, circular helix, like this type of circular helix. Now if you add those points, then you will get this type of continuous graph. Okay. Now in this example, we have r of t equals to t cosine t, t sine t, t, and we need to sketch it. So when t is 0, this one becomes 0 0 0, and when t is pi over 2, then as before you will get 0 pi over 2, and we know the value of pi is 3.14. So 3.14 over 2 is 1.6. This one also 1.6, and similarly you will get other points on 3 dimension. If you plot those points, then you will get this type of path, That means you will get this type of path. Now the projection of this graph on the xy plane is this one. Now to understand this, suppose you flash a light from above. Then the shadow of this graph on the xy plane would be like this. Okay, like I'm looking the graph from above, then it will be like this. And this is called the projection of the graph on the xy plane. Suppose we have the vector function r of t equals to this one, and we need to find its domain. So this first component, this one would be valid if t plus 1 is more than or equal to 0. So if t plus 1 is more than or equal to 0, that means t is more than or equal to negative 1. So t is more than negative 1. And second one would be valid if t is not 0. So for second one, t can be any value except 0. Okay. And third one would be valid if 4 minus t square is more than 0. That means t is between negative 2 to positive 2. So if you solve this, it would be between negative 2 to positive 2. Now, which region overlap? You will see that this region from negative 1 to positive 2 overlap except at 0. So the domain would be negative 1 to 0 union 0 to 2. This is open interval. It means this 0 is not included. In calculus 1, you learned how to find limit of a function, but now we will learn how to find limit of a vector function. Suppose you have a vector function r of t equals to x of t, y of t, z of t, and we want to find limit at a. Now, limit of this vector function will exist if limit of all component exist. That means if all of them limit exist, only then limit of this vector function will exist. If any of them doesn't exist, then the limit of the vector function will not exist. To clarify this, we will discuss few examples. In this example, we need to find the limit. So when t approaches 1, limit of first component is 1. We apply L'Hopital's rule here because this is 0 over 0 form. And when t approaches 1, limit of second component is 3. And when t approaches 1, limit of third component is negative pi. We also apply here L'Hopital's rule because this is 0 over 0 form. Remember, you can apply L'Hopital's rule only if it is 0 over 0 or infinity over infinity form. So limit of first component is 1, so it becomes 1i or just I. Limit of second component is 3, so it is 3j, and limit of third component is negative pi, so it is negative pi k. So limit of this vector function is I plus 3j minus pi k. Now in this example, limit of first component, we use L'Hopital's rule because this is infinity over infinity form, and we got negative 1. And limit of second component, so when t approaches infinity, this one becomes tan inverse infinity, which is pi over 2. This is a finite value, so limit exists. And limit of third component also 0, and 0 is a finite value. Therefore limit of the vector function is negative 1i plus pi over 2j plus 0k, or even you can write in this form. Now in this example, when t approaches 1, limit of first component is 1. When t approaches 2, limit of second component is 1 over 2. We also apply L'Hopital's rule here. But when t approaches 1, this limit doesn't exist. Now, since one of them limit doesn't exist, so the whole limit doesn't exist. That is, since L3 doesn't exist, so the whole limit does not exist. That's it for today's class. We'll discuss more on next class. Stay safe.